Right now there are just millions of people driving at like 70 miles an hour down the highway.
Yeah, totally oblivious to what's under them.
Right. They're sitting directly on top of this completely sealed chemical environment that is, frankly, containing massive amounts of volatile energy.
A huge amount of energy. It's essentially a controlled chemical reaction.
Exactly. And, if something goes wrong deep inside that sealed box, I mean, if a single drop of highly corrosive acid leaks or like a microscopic spike of metal grows just a millimeter too long.
The driver usually has absolutely no idea.
None. The warning light on your dashboard pops up, and it might just look like a harmless computer glitch,
Yeah,
right?
just a little amber light.
And you might think, oh, I'll just have the mechanic reset the sensor. No big deal.
Which is such a dangerous assumption.
It really is.
Yeah.
Today, we're going to show you why that specific assumption could be, well, the most expensive and potentially dangerous mistake you can make with a modern electric vehicle.
It's a complete paradigm shift, really.
Yeah, explain that a bit. What are we shifting away from?
Well, we're moving away from the era of mechanical wear and tear, like where a broken steel part is just visibly broken. You can look at it and see it snapped.
Like a snapped timing belt or a rusted muffler.
Right. We're moving from that into a world of completely invisible electrochemical decay. And to understand how the elite engineers in the industry are handling this shift, we're digging into an incredible piece of source material today.
Yes, we are. And I want to give a shout out to this document because it is a massive 80-page engineering masterclass. The original title is actually DMO, Valium Berthwood, BMS, Turin.
Which is a very dense title.
Very dense. For our deep dive today, we're translating that as EV high voltage battery systems and battery management system, failure analysis and prevention strategies.
And when we say this is highly technical, I mean it is hardcore.
Oh, it's a beast. It's just a dense matrix of acronyms, chemical formulas, software algorithms. I mean, it frankly reads like a foreign language if you aren't a working material scientist.
Which is why we're breaking it down today.
Exactly. That is our mission. We are going to decode the exact DNA of EV battery failures for you. We're going to explore how these battery forensics teams actually hunt down these invisible electrical killers.
And we're going all the way down to the physical hardware limits, right down to the microscopic level.
Yep, and then traveling all the way back up to the advanced software algorithms that are just frantically trying to predict this chemical decay in real time. So, if you stick with us, you're going to understand EV batteries better than your local mechanic by the end of this.
Honestly, probably a lot better. Because this document doesn't pull any punches about where the current mechanic industry is failing.
Right. It starts by identifying this massive industry-wide blind spot.
This methodology that's just been carried over from legacy gas-powered cars, and it is completely failing when they try to apply it to high-voltage EV systems.
So let's start right there. Because for decades, the standard operating procedure for a car acting up was, well, pretty straightforward.
Yeah, it was simple.
Your gas car throws a check engine light. You take it to the mechanic or like an auto parts store.
They reach under the steering wheel.
Right. They reach under, they plug in that little plastic OBD scanner, the onboard diagnostics thing, and they pull a code.
And maybe it's a code for an oxygen sensor running a little lean. Right.
Exactly. And what do? 90% of the time, they hit a button that says clear codes. They reset the computer. And they look at you and say, let's just see if the light comes back on.
Which, I mean, in the context of an internal combustion engine is actually a somewhat defensible strategy.
Wait, really? It's not just lazy mechanics?
No, not always. I mean, a gas engine is fundamentally just a collection of heavy metal parts moving in a very specific sequence, right? And it's monitored by a few external sensors.
Okay, that makes sense.
So sometimes the sensor just gets a temporary bad reading. Maybe you hit a massive pothole or you just didn't tighten the gas cap enough.
Oh, I've done the gas cap one.
We all have. Or maybe there was a momentary misfire because of a bad drop of fuel. So you clear the code, the sensor resets its baseline, the metal parts keep spinning, and the car is perfectly fine.
But doing that on an EV is different.
The engineering masterclass points out that applying this clear and see logic to an EV high-voltage system is a catastrophic error.
Because we aren't dealing with dumb metal parts anymore.
Exactly. Relying solely on reading those OBD codes, whether they're the P codes for powertrain issues or the U codes for network communications, it entirely ignores the physical and chemical realities happening inside that sealed battery pack.
You just can't software update your way out of degraded chemistry.
Right. You cannot just hit a reset button on a chemical reaction.
So the document provides some really stark examples of what happens when a technician falls into this trap, and I want to look at one of the network communication errors it brings up.
The inverter interference one?
Yeah, that one. So the document describes the scenario where a mechanic plugs in a scanner and pulls a U code. And this code indicates an inverter communication interference.
And just to clarify for everyone, the inverter is the heavy-duty component that takes the direct current, the DC power from the battery, and transforms it into the alternating current, the AC power.
Right, the power that the electric motors actually use to propel the car forward.
Exactly. It's a crucial piece of hardware.
So the scanner is basically telling the mechanic, hey, the main computer cannot talk to the inverter properly. If a traditional mechanic sees that, what is their instinct?
Well, a mechanic trained on legacy diagnostic trees might look at that code, see that the high-voltage system has a fatal communication failure, note that the battery management system is totally unresponsive, and just conclude the absolute worst.
They just assume it's dead.
Right. They might decide that the entire high-voltage battery pack is completely compromised and order a $15,000 replacement.
But the authors of our source material highlight how often this is just a fatal misjudgment.
Because they're trusting the software's interpretation of the problem without investigating the physical world.
They're just looking at the screen.
Precisely. I mean, the battery pack itself, all the lithium, all the individual cells might be perfectly healthy. The real issue driving that communication interference code could be something incredibly mundane.
Like what?
It could just be electromagnetic interference caused by a completely unrelated low-voltage wire rubbing against the metal chassis of the car, which creates network noise.
Wow.
Or it could be a faulty grounding strap on the metal housing of the inverter.
So it's just a loose wire making the computer think the battery is dead.
Exactly. By just reading the code and taking the software alert at face value, the technician entirely misses the physical reality, and that results in a massive unnecessary expense.
They are basically recommending a heart transplant when the patient just has like a pinched nerve in their arm.
That's a great way to put it.
But the document points out that this diagnostic blind spot goes the other way too, right? Like sometimes the code makes the problem look like a minor software glitch, but the physical reality is actually terrifying.
Yes. The text spends a lot of time talking about the danger of ignoring micro leaks of electrolyte.
This part was wild to me. It's one of the most critical warnings in the entire text.
So an OBD scanner might show a very subtle, intermittent isolation fault.
Okay, let's define that. An isolation fault just means that the high voltage electricity inside the battery is somehow finding a microscopic, unintended pathway to the metal chassis of the car, right?
Correct. The electrical isolation is essentially broken down.
And a traditional mechanic might see that intermittent fault and think, oh, it rained really heavily yesterday. It's a humid day. There's probably just a little condensation on a wiring harness somewhere.
Right, they think it's just water.
So they clear the code, assume the moisture will evaporate, and tell you the car is good to go.
And that assumption is exactly what the engineers writing this document are terrified of.
Why? What's actually happening?
Because what that subtle isolation fault might actually represent is a micro leak of the liquid electrolyte from inside one of the battery modules.
Okay, I think we need to clarify what electrolyte actually is because, when I hear that word, I immediately think of a sports drink. I think of Gatorade.
Right, replenishing your electrolytes.
Yeah, but battery electrolyte is absolutely nothing like spilling a little washer fluid or Gatorade, is it?
Not at all. The electrolyte inside a lithium-ion battery is a highly volatile, highly corrosive, and highly flammable organic solvent.
Okay, so it's nasty stuff.
Very. Its job is to transport lithium ions back and forth between the positive and negative sides of the battery. If a cell casing develops a microfracture and this solvent leaks even in amounts so microscopic you wouldn't even notice a puddle, it begins to silently eat away at the internal environment of the battery pack.
It's actively destroying the system from the inside out.
Exactly. It corrodes the delicate circuit boards, it degrades the plastic insulation around the high-voltage wiring, and it compromises the structural integrity of all the surrounding cells.
And this happens slowly, right?
Over the course of months, yeah. That ignored microleak, the one the mechanic assumed was just humidity, slowly turns into a massive safety hazard. It creates the perfect conditions for a short circuit, which leads to a thermal event.
And thermal event is just the polite corporate engineering term for a catastrophic battery fire.
Yes.
Yeah.
A very large, very hard to extinguish fire. And ultimately, it results in a colossal warranty cost for the manufacturer and a massive danger to the driver.
Which is exactly why the authors emphasize that when a mechanic just clears the code on an EV without investigating the physical cause, they aren't fixing anything.
They're essentially putting a Band-Aid on a chemical wound that is actively bleeding.
They're silencing the fire alarm while the smoke is still filling the room.
Perfectly said.
And this is exactly why you, the listener, need to care about this distinction. If you own an EV or, plan to own one soon, understanding this fundamental difference in diagnostics is what separates a $50 software reset from a $15,000 nightmare.
You simply cannot treat a high-voltage battery system like a 1998 Honda Civic with a loose gas cap.
You really can't. So, if the old way of plugging in a scanner is broken, what is the right way? How do these elite engineers who wrote this 80-page masterclass actually hunt down these failures?
Well, because they know the traditional methods are failing, they developed a highly rigorous, highly structured methodology to break through these diagnostic blind spots.
The document calls it the four-piece closed-loop analysis.
Yes, it is essentially the definitive guide to performing an autopsy on a dead electric vehicle.
I want to spend some real time walking through these 4 steps because the sheer scale of the investigation is just fascinating to me.
It's a huge process.
It moves from the massive physical structure of the car all the way down to the atomic level. So let's start with step 1, macro analysis. This is looking at the system level before you even think about looking at a microchip, right?
Correct. Before you can analyze the microscopic chemistry, you have to establish the integrity of the macro-level physical boundaries.
The big stuff.
Right. The engineers are looking at the high-voltage boundaries and the massive physical pathways where current flows. Step 1 is a highly detailed physical inspection looking for macroscopic trauma.
And the source material gives some very vivid, almost violent examples of what to look for during this macro analysis.
It does get pretty intense.
The first thing it mentions is checking for compromised pack airtightness. Now, I always think of an EV battery pack as essentially a sealed submarine bolted underneath the floorboards of the car.
That's a good way to picture it.
It has to be completely airtight because if it's not, water and road salt get inside, and high voltage mixed with salt water equals a very bad day.
A very bad day.
But the next macro level check it mentions sounds much more intense. It says engineers must look for sandblasting on the explosion-proof valves.
Yes.
What exactly are those valves and how do they get sandblasted? That sounds crazy.
Okay, so every EV battery pack is equipped with specialized pressure relief valves, which the industry often calls explosion-proof valves or venting valves. You have to remember that a battery pack is a tightly sealed metal box. If a cell inside that box goes into thermal runaway, meaning it overheats uncontrollably and catches fire, it doesn't just burn. It rapidly produces a massive volume of incredibly hot, highly toxic gas.
And if that gas has nowhere to go, that sealed metal box essentially becomes a pipe bomb.
Exactly. To prevent the entire battery casing from structurally rupturing or exploding from the sheer pressure, these valves are designed to burst open at a specific pressure threshold.
So they let the gas out.
Right, venting the gas out of the pack safely away from the passenger cabin. Now, the gas that comes shooting out of these valves isn't just hot air.
What's in it?
It is a dense, high-velocity mixture of vaporized heavy metals, carbon soot, and boiling electrolyte mist.
Oh, wow. So it's like a blowtorch mixed with a sandblaster.
Yes. So if an engineer is inspecting a battery pack that looks totally fine on the outside, but they look closely at that venting valve and see that the metal around it is heavily pitted, scarred, and covered in a thick layer of high-velocity particulate residue,
They know instantly what happened.
they know, beyond a shadow of a doubt, that a catastrophic high-pressure thermal event occurred inside that pack.
It's like finding heavy soot around the muzzle of a gun. You don't need to see the bullet to know a shot was fired.
That is a perfect analogy. The physical evidence of the trauma remains.
Okay, so what else are they looking for on the outside?
Another key check during this macro analysis is looking for what the document calls massive electrical arc sintering on contactors.
Okay, I'm looking at that phrase. Massive electrical arc sintering. I know a contactor is essentially a heavy-duty switch that turns the battery's power on and off, right?
Right, it connects the battery to the car.
But arc sintering sounds like a term out of an industrial welding shop. What is physically melting inside the car to cause that?
To understand arc sintering, you really have to picture the scale of the energy we are dealing with. Think of a contactor as a giant electromagnetic relay switch that connects the 400 or 800 volt battery to the rest of the vehicle.
Okay, so it's a huge switch.
When you press the start button in your EV, you often hear a very distinct solid clunk coming from the back of the car.
Yeah, I've heard that.
That noise is the physical metal plates of the contactors violently slamming shut to allow the high voltage power to flow.
It's like the drawbridge coming down.
Right. But imagine a scenario where something goes terribly wrong.
Mm.
Say there is a massive short circuit somewhere in the drive unit. The car's safety systems panic and attempt to instantly open those contactors to cut the power.
To protect the car.
Exactly.
Huh.
But they're trying to open a switch while hundreds of amps of current are actively flowing through it. Electricity at that voltage and amperage has immense momentum. It doesn't want to stop just because the switch is pulling apart.
So it jumps the gap.
It violently jumps through the air between the separating metal plates, creating a sustained electrical plasma arc.
Ah, plasma arc.
And this arc is incredibly hot, often hotter than the surface of the sun for a fraction of a second.
It's literally a lightning bolt trapped inside a plastic switch housing.
Precisely. And that extreme localized heat instantly melts the heavy copper and silver contacts inside the switch.
Oh, man.
As the switch continues to pull apart, the molten metal cools almost instantly, effectively welding the switch permanently in whatever jagged half-open or half-closed position it was in.
And that process is the arc sintering.
That process of melting and fusing under an electrical arc is called arc sintering. So if an engineer opens the pack, cuts open a contactor, and sees that the metal plates are melted and fused together in a burnt, blackened mess, they have found undeniable macro-level physical failure.
The car tried to stop the power, but it was just too strong.
The vehicle safety system tried to save itself, but the sheer kinetic energy of the electricity overpowered the physical hardware.
That is incredible and terrifying. Okay, so that is step one. You look for the big violent failures, but what if the pack looks clean?
Right, what if there's no obvious damage?
Yeah, what if there's no sandblasting and the contactors are fine? That brings us to step two of the analysis. Microanalysis. If the macro level is clean, they zoom in. This step is about extreme precision. The text says engineers are hunting for invisible circuit killers on the PCBA, the printed circuit board assembly.
This is where the investigation shifts from looking at the muscle of the battery to examining its sensory nervous system.
The sensors.
Right. The document focuses heavily on the intricate inspection of the AFE, or analog front-end chips, as well as the microscopic pins and the ultra-thin cables connecting them.
Let's define the AFE chips for a second. These are the tiny microchips scattered throughout the battery pack that are responsible for actually measuring the voltage and temperature of every single individual battery cell, right?
Yes. If the mass of battery cells are the muscle fibers, the AFE chips are the millions of delicate nerve endings, reporting back exactly how much tension and heat is in every single fiber.
They're the eyes and ears of the car's brain.
They are the eyes and ears of the battery management system. But because they are highly sensitive electronics living inside a harsh automotive environment, they are incredibly delicate.
And you can't just look at them with a magnifying glass.
No, the document notes that engineers cannot simply look at these boards with the naked eye. They must use specialized tools like 3D AOI automated optical inspection.
I actually had to look up how 3D AOI works, and it's fascinating. It doesn't just take a flat picture. It uses lasers and multiple cameras to map the three-dimension topography of the circuit board down to the micron.
It's incredibly precise.
It's looking for tiny shadows. Why do they need that level of detail?
Because they're hunting for microcracks in the solder joints that connect these tiny chips to the board. We are talking about fractures that are thinner than a human hair.
How do those even happen?
These cracks can be caused by the constant low-frequency vibration of driving down a bumpy road for 3 years, or they can be caused by the thermal expansion and contraction of the board, constantly heating up and cooling down.
So just normal driving wears them out.
Over time, yes. If a solder joint develops a microcrack, the AFE chip loses its connection to the battery cell. It goes blind.
And if the BMS is blind, it can't safely manage the battery. And while we are talking about microscopic damage to these circuit boards, I have to bring up a phenomenon from the text that genuinely blew my mind.
Oh, the capillary siphon effect.
Yes, the capillary siphon effect. When I read how this physically works inside the car, it sounded like a horror movie for electronics.
It is a brilliantly insidious physical mechanism.
Yeah.
Walk me through how you visualize it happening based on the text.
Well, okay, the best analogy I could think of is paper towels.
Okay, I like it.
Imagine you spill a little water on your kitchen counter. You take a dry paper towel and you just dip the very corner of it into the puddle. You don't push it down, you just let it touch.
Right.
What happens? You watch the liquid fight gravity. It creeps up, up, up the paper towel, completely soaking it, moving vertically away from the spill.
The liquid is pulled upward by surface tension.
Exactly. Now, the document says that if a battery cell down at the bottom of the pack develops a tiny micro leak of that highly corrosive liquid electrolyte we talked about earlier.
The dangerous solvent.
Right. The liquid doesn't always just harmlessly pool on the metal floor of the battery casing. Because the battery cells are connected to the circuit boards mounted high above them by tightly bundled, insulated wire harnesses, the liquid electrolyte touches the exposed tip of the copper wire at the cell terminal. And then through that capillary siphon effect, the corrosive liquid literally gets pulled up the inside of the wire insulation, fighting gravity, siphoning inch by inch all the way up to the circuit board mounted at the top of the pack.
It uses the microscopic air gaps between the hundreds of twisted copper strands inside the wire as a capillary tube.
Right. It's like this toxic, corrosive sap creeping up the stem of a plant.
It is exactly like that.
And it happens completely invisibly inside the plastic wire casing. It can take months. But eventually, that corrosive electrolyte reaches the top of the wire, spills out onto the delicate microchips of the circuit board, and chemically corrodes them to death.
Your paper towel analogy perfectly captures the mechanism. And this highlights exactly why the traditional OBD scanner diagnostic fails so spectacularly here.
Because the scanner would just say the board is dead.
Right. A mechanic plugging in a scanner would just see a U code on their screen saying BMS internal communication fault. They would assume the circuit board itself just had a random electronic glitch, replace the board, and send the car on its way.
They would have absolutely no idea that the real root cause was a microscopic chemical leak 3 feet away that climbed a wire like a spider.
Without the microanalysis step, the new circuit board will just get corroded all over again.
Which perfectly illustrates why you need this rigorous methodology. You have to look at the micro level.
You really do.
Okay, moving deeper into the autopsy. We've looked at the macro system, we've looked at the microscopic circuit boards. Now, step 3. Metallographic and material analysis.
This is where it gets really scientific.
Yeah, we are leaving the realm of electronics and entering the realm of chemistry and atomic structure.
This step is fundamentally about proving irreversible physical destruction.
Proving the battery is actually dying.
Exactly. If an electric vehicle is experiencing a severe loss of range, engineers need to answer a critical question. Is this just a software calibration error where the car thinks it's out of energy? Or is the physical battery chemistry actually degrading and dying?
And how do they figure that out?
To answer this definitively, they rely on millions of dollars of laboratory equipment. The document specifically mentions the use of SEMBA, a scanning electron microscope, and EDS, energy dispersive spectroscopy.
Okay, I have to stop you there because we need to ELI 5 explain it like I'm 5 how EDS actually works.
Okay, fair enough.
I understand that an electron microscope uses a beam of electrons instead of light to see things that are incredibly tiny, like the surface of a single cell. But what does energy dispersive spectroscopy do? It sounds like something a Star Trek medical tricorder would use.
It's actually not far off from a tricorder, to be honest. Yeah. When you look at something under a normal scanning electron microscope, you are essentially getting a highly detailed black and white topographical map. You can see the shapes of the structures, but you don't necessarily know what they're made of. A bump is just a bump.
Okay, so you just see the outline.
What EDS does is fire a highly focused beam of X-rays at that microscopic bump. When the X-rays hit the atoms of the material, those atoms get excited and eject their own X-rays back at the sensor.
Wait, they shoot X-rays back?
They do, and they bounce back with a specific energy signature. Every single element on the periodic table, carbon, oxygen, lithium, copper, emits a uniquely identifiable X-ray energy signature when hit.
So it's like a fingerprint.
Exactly. The EDS sensor reads those returning X-rays and allows the engineer to color-code the microscopic image by element.
That is wild.
So you aren't just seeing a strange microscopic lump on the battery anode. The EDS tells you, hey, this lump is composed of pure metallic lithium, and it's surrounded by oxygen and fluorine.
It gives you the exact chemical makeup of the failure at an atomic scale.
It lets them see the exact chemical footprint of the crime scene.
And what exactly are they hunting for with these $1 million tools? The source material highlights 2 massive red flags that engineers look for during this material analysis.
Abnormal thickening of the SEI layer and the growth of lithium metal dendrites.
Let's break these down, starting with the SEI layer, the solid electrolyte interface.
This is a crucial concept in battery chemistry. You can think of the SEI layer as a foundational protective barrier. It actually forms naturally on the graphite anode of a lithium-ion battery during its very first, carefully controlled charge at the factory.
So it's supposed to be there.
It is absolutely necessary for the battery to function. Without this layer, the highly reactive liquid electrolyte would constantly attack and dissolve the graphite anode.
Now, I've seen it described before as a scab forming over a wound, like the battery cuts itself, forms a scab, and it's protected.
I've heard that one.
But I don't think that analogy quite works, does it? Because a scab implies a temporary healing process. Eventually, a scab falls off and fresh skin is underneath. The SEI layer doesn't fall off.
You're right, the scab analogy falls short. A better way to visualize the SEI layer is to think of the calluses on the fingertips of a professional guitar player.
Oh, I like that. That makes sense.
When you first start playing guitar, the steel strings tear up your fingertips. It hurts. So your body builds up a thin, tough layer of callus.
To protect the skin.
Right. That thin callus is perfect. It protects the soft tissue of your finger, but it's still thin enough that you can feel the strings and play the instrument effectively.
So that is a healthy SEI layer.
Exactly. It protects the anode, but it's thin and porous enough to allow lithium ions to easily pass through it back and forth as you charge and discharge the battery.
But what happens over time? Because it doesn't stay thin forever, right?
Just like a callus. If you expose the battery to constant excessive stress, massive heat, aggressive fast charging, deep discharging, that protective layer reacts by growing thicker and thicker to protect the anode.
And that's bad.
And as it grows thicker, it starts to cause massive problems. First, a thick callus is numb. You can't feel the guitar strings anymore. In the battery, a thickened SEI layer makes it incredibly difficult for the lithium ions to push their way through to store energy.
The internal resistance skyrockets.
Precisely.
And doesn't the thick layer also physically trap the lithium ions inside itself?
Yes, that's the real killer. The material that makes up that thickened layer is literally built out of active lithium ions that got stuck.
So they're just trapped there forever.
Once they are trapped in that layer, they can no longer participate in storing or releasing energy. The battery's physical capacity permanently shrinks.
So, if an engineer uses a scanning electron microscope, an EDS, and they observe that the SEI layer has grown excessively thick and is hoarding lithium, that provides objective, undeniable proof that the battery has permanently lost capacity.
It is not a software glitch. The battery has chemically aged and degraded.
It's like finding out the fuel tank on your car physically shrank.
That's exactly what it's like.
Okay, that's the first red flag. But the second red flag they look for, the lithium metal dendrites, sounds significantly more dangerous.
It is the ultimate nightmare scenario for battery engineers.
The text explicitly links the formation of dendrites to a very specific driver behavior. Low temperature fast charging.
Yes.
Explain the physics of that. Why does cold weather plus fast charging equal a nightmare?
Okay, so in a healthy battery during a charge, lithium ions swim through the electrolyte and smoothly embed themselves into the porous structure of the graphite anode. It's like finding an empty seat in a movie theater.
Everyone just walks in and sits down.
Right. But when the battery is freezing cold, the chemical reaction slows down dramatically. The structure of the graphite essentially tightens up.
The seat sits smaller.
Basically.
Yeah.
If you pull up to a 250 kilowatt DC fast charger in the dead of winter and try to force massive amounts of energy into that freezing battery, the lithium ions can't slide into the graphite seats fast enough.
There's a bottleneck at the entrance.
Exactly. Because they can't get inside the anode, the lithium ions start piling up on the outside surface of the anode. And as they pile up, they begin to bond together, forming pure metallic lithium.
And this process is called lithium plating.
Yes. Over time, as this plating continues, it doesn't just grow as a flat sheet. It starts to grow outward in microscopic, needle-like metallic spikes.
Oh, wow.
These jagged metal spikes are the dendrites.
So by forcing high power into a cold battery, you are essentially growing microscopic stalagmites of solid metal inside the cell.
Yes, and these metallic stalagmites are highly conductive and razor-sharp at a microscopic level.
Razor sharp? That can't be good inside a battery.
It's terrible. If you continue to abuse the battery, these spikes will grow longer and longer until they eventually pierce right through the ultra-thin plastic separator membrane that physically divides the positive and negative sides of the battery cell.
And if they pierce that separator,
You get an internal micro short circuit. The positive and negative sides are now physically connected by a wire of pure lithium.
the battery just shorts itself out.
The battery begins bleeding its own energy internally.
dumping all that stored power into a tiny, localized point, creating massive, intense heat.
Which causes a fire.
This localized heat boils the electrolyte, generates gas, and often triggers catastrophic thermal runaway. When an engineer puts a dead cell under an electron microscope and finds a dendrite piercing the separator, it is exactly like finding the murder weapon at a crime scene.
It definitively proves exactly how and why the cell died.
It takes all the guesswork out of it.
It is a fascinating investigative process. But, it raises a huge logistical question for me.
What's that? Well, the first three steps of this closed-loop analysis, the macro inspection, the microcircuit board span, the electron microscope material analysis, they all require physically tearing the battery pack apart.
They do.
You have to essentially dissect the car to find these clues, but automakers are producing millions of these vehicles. You obviously cannot perform $1 million physical autopsy on every single car that throws a warning light on the highway.
No, you definitely can't. Which is exactly why Step 4 is the crucial, revolutionary link in modern diagnostics.
Step 4 is data comparison. Software versus reality.
This is where the true magic happens, and it happens without a mechanic ever picking up a wrench or opening the battery pack.
How does that work? How do you see inside the battery without opening it?
Through the immense power of high-frequency telemetry, every modern electric vehicle is effectively a rolling data center.
They're constantly connected.
They are constantly streaming gigabytes of telemetry data back to the manufacturer's cloud servers in real time. We're talking about highly granular data. The voltage, current, and temperature of every single cell module recorded at millisecond intervals over the entire lifespan of the vehicle.
The source material uses a very specific, almost mathematical term here. It says the engineers analyze this cloud data to look for algorithm residuals.
Yes.
It defines that as instances where the physical reality of the battery diverges from the mathematical prediction. Can you explain what a residual is in this context?
Sure. Inside the battery's central computer, the battery management system software is constantly running a highly complex mathematical simulation of the physical battery.
Like a digital clone.
It maintains an idealized digital twin of how the chemistry should be behaving at any given moment, based on the current temperature and the amount of power the driver is demanding. This mathematical simulation is called the ECM, or the equivalent circuit model.
Okay, so the computer has a perfect theoretical map of the battery.
Exactly.
Yeah.
Now, imagine you are driving on the highway, and you step aggressively on the accelerator pedal to pass someone. The mathematical ECM model instantly calculates, based on my formulas for a healthy battery at this temperature, delivering this much power should cause the overall voltage to drop by exactly 10 volts during the acceleration.
That is the prediction.
That is the prediction. But simultaneously, the physical voltage sensors inside the battery measure what is actually happening. And the cloud data shows that the actual physical voltage of the battery plunged by 25 volts.
So the math was wrong. The prediction failed.
Yes. The difference between the software's prediction, a 10-volt drop, and the physical reality, a 25-volt drop, is the residual.
The gap between the two.
The algorithm's math no longer matches the physical world. The document refers to this growing gap as ECM parameter drift.
It's the classic saying, right? The map is no longer the territory. The software's idealized map of the battery no longer matches the physically aged, degraded reality of the actual cells.
Precisely. The document details how engineers hunt for these anomalies in the cloud data. They look for distortions in the pre-charge RC time constant, or instances where the extended Kalman filter algorithm fails to match the actual polarization voltage drop.
Okay, I have to pause here. The extended Kalman filter.
Zip term.
When I read that in the text, it sounded like an algorithm they would use in a NASA mission control room, not in a family sedan.
Well, it is actually deeply rooted in aerospace engineering.
Wait, really?
Yeah. The Kalman filter was famously utilized during the Apollo space program in the 1960s. It was absolutely essential for helping track the trajectory of the lunar module and the command module.
Are you serious? How does rocket science translate to a car battery?
Fundamentally, a Kalman filter is a highly advanced predictive algorithm designed to estimate the true state of a system when you can't observe it directly and when the sensors you do have are noisy or imperfect. In the Apollo program, they couldn't run a physical measuring tape from the Earth to the Moon. They had to take a mathematical guess at where the spacecraft was, take a MECE radar sensor measurement, compare the two, and then mathematically update their next guess to be slightly more accurate.
So it's a continuous loop of predict, measure, correct.
Exactly. And how is that happening inside an EV?
Well,
In an electric vehicle, you cannot directly physically measure the chemical state of charge or the state of health of a battery cell. You can't stick a dipstick into a sealed lithium cell to see how much fuel is left.
Right. It's sealed.
You can only measure the external voltage, the current, and the temperature, and those sensor readings are often messy and noisy.
So the car's computer is treating the internal chemistry of the battery like a spacecraft millions of miles away.
Exactly. The extended Kalman filter inside the BMS is constantly taking a mathematical guess at the exact chemical state of the lithium ions, measuring the external voltage, and updating its guess. It is continuously striving to predict the invisible chemistry.
That's just phenomenal.
When the engineers look at the cloud data and see that the Kalman filter's predictions are starting to wildly and consistently disagree with the actual sensor measurements, they know without a doubt and without ever opening the pack that the physical chemistry of the battery is fundamentally breaking down.
Because the physical reality has drifted too far away from the math?
Exactly. They are using Apollo-era spaceflight mathematics to track the microscopic decay of lithium ions in real time.
And that completes the four-piece analysis, moving from the macro explosion valves to the microcircuit boards, down to the atomic structure under an electron microscope, and finally up into the cloud data comparing math to reality.
It really shows how far beyond a simple check engine light we have evolved.
The immense complexity of the system demands this level of rigor, but having all this data creates a new problem.
What's that?
How do you organize it? I mean, if a car is throwing a dozen different warning codes, how do engineers keep from going insane chasing ghosts in the machine?
Which brings us to the next massive concept in the source material. Section 3, essentially, organizing the chaos.
A very necessary section.
The document introduces a comprehensive system architecture designed to map out 24 core complex fault codes. And it does this using what it calls the top-down and MECE principle.
MECE. It is an acronym that stands for Mutually Exclusive, Collectively Exhaustive.
I've heard that used in business before.
Yes, it is a highly disciplined logical framework that is heavily utilized in management consulting, like at McKinsey, and in complex systems engineering.
Break that down for us. What does it mean to be mutually exclusive and collectively exhaustive in the context of a car?
It means that you have created a categorization system where every single possible failure that could ever happen to the car fits perfectly into one and only one category.
So no overlaps.
There's absolutely zero overlap between the categories. That's the mutually exclusive part. And there is no possible failure left unmapped. That's the collectively exhaustive part. You have successfully mapped the entire known universe of what can go wrong.
So if a car experiences an intermittent voltage drop, you don't just blindly start replacing parts.
No, you use the MECE map to ask highly targeted questions.
Like, is the physical battery cell dying? Or is the sensor reading the voltage broken?
Or is the wire transmitting the sensor data snapped? Or is the mathematical software calculating the voltage wrong?
Exactly. If you don't rigidly organize the physical and digital geography of the car, you will chase symptoms forever without ever finding the root cause.
To achieve this, the document breaks the entire EV high-voltage ecosystem down into 5 distinct dimensions.
Let's walk through these 5 dimensions to give you, the listener, a mental map of the vehicle's architecture. I want to build the car from the ground up.
Sounds good. Let's do it.
Dimension 1 is the battery body and electrochemical layer. This is the absolute foundation. The physical lithium, the liquid electrolyte, the graphite anodes. This is the absolute limit of the system's physical energy.
It is the raw muscle of the car.
Right. Dimension 2 is physical sensing and front-end collection. This is the sensory hardware. The physical temperature probes taped to the cells, the voltage taps, the delicate AFE microchips we talked about earlier. This dimension just observes the muscle and gathers data.
It is the peripheral nervous system.
Love that. Dimension 3 is the electrical circuit and communication control. This is the data highway, the low-voltage wiring harnesses, the CAN bus network, the physical pathways that carry the sensory data from the battery pack to the main computer.
The spinal cord of the vehicle.
Dimension 4 is software algorithm and logic control. This is the brain, the diagnostic and protective soul of the car. This is where the extended Kalman filters live, where the mathematical ECM models run, and where the decisions are made.
The frontal lobe, processing the data and deciding how to react.
And finally, Dimension 5 is system high-voltage execution and global security. This is the heavy physical hardware that enforces the software's decisions. The massive metal contactors, the explosion-proof valves, the physical isolation barriers that keep the 400 volts of electricity from shocking the passengers.
The physical bouncers at the door, keeping everyone safe when things go wrong. Every single complex fault code in a modern electric vehicle maps perfectly to a failure in one of these 5 specific dimensions.
And for the remainder of our deep dive today, we are going to use this MECE map to zoom all the way down to the absolute bottom, the root of all power and the ultimate source of failure, Dimension 1.
The electrochemical layer.
This is where the real drama happens, because this is the battleground where the immutable laws of physics and chemistry wage war against the driver's demands for speed and range.
The document introduces us to a very specific, very common fault code that originates right here in Dimension 1.
It is DTC P0A0. This code translates on a scanner to weak cell or a recommendation for battery pack replacement.
And the engineering text describes the physical phenomenon behind this code as the wooden barrel effect.
The wooden barrel effect. I love this analogy.
It's an elegant way to describe a concept formerly known as Liebig's law of the minimum. I want you to imagine an old-fashioned wooden barrel, the kind used to age wine, made out of dozens of vertical wooden planks or staves banded together.
Okay, I'm picturing it.
But imagine that these staves are not all the same height. Some are tall, some are medium, and one stave is cut completely in half. It is much shorter than all the others. How much water can that barrel actually hold?
It doesn't matter how tall the other staves are, it can only hold water up to the exact height of the shortest stave. As soon as the water reaches that point, it just spills out the side.
Exactly. The capacity of the entire barrel is entirely dictated by its weakest, shortest link. An EV battery pack operates on the exact same physical principle.
So a high-voltage battery is not one giant monolithic tub of energy.
No. It is constructed of hundreds and sometimes thousands of individual small battery cells all wired together in a massive series circuit.
So let's say you have a battery pack made of 100 individual cells. 99 of those cells are perfectly healthy. They are tall staves. They can hold 100% charge. But just one single cell out of the 100 has degraded. It has become a weak cell and can only hold an 80% charge. What happens to the car?
Your entire vehicle is now an 80% car.
Just because of one cell?
Yes. That single weak cell is the shortest stave in the barrel. Because they are wired in series, the flow of electricity is dictated by that weak link. It drags down the maximum output power and the total usable capacity of the entire 100-cell pack.
And the battery management system is constantly watching for this, isn't it? The text notes that if the software detects that the static or dynamic voltage difference between the highest cell and the lowest cell stays above a 20% safety limit for a certain amount of time, the car throws the P2A80 error code.
It does.
But what does the driver actually experience when the wooden barrel effect triggers on the highway? Like, what does it feel like?
The driver experiences a very sudden, very frightening change in vehicle behavior.
Yeah.
The most immediate shock is the dashboard estimation.
The range drops.
The range on the screen might drop off an absolute cliff. You could be driving, thinking you have 150 miles of range left, and in the blink of an eye, the dashboard recalibrates to that single weak cell and says you have 20 miles left.
That would induce instant panic. I'd be terrified.
It does. And it's not just a software update. The physical performance of the car changes instantly, too. If you press the accelerator pedal, you will lose sudden acceleration. The car will feel incredibly sluggish, heavy, and unresponsive.
Why does it do that?
Ultimately, to protect that single weak cell from overheating and catching fire under load, the BMS software will force the car into what automotive engineers call limp home mode.
Limp home mode.
The car drastically restricts torque and top speed, essentially turning your high-performance EV into a golf cart, just to ensure you can safely limp to the shoulder of the highway or to a service center.
It's an extreme act of self-preservation by the software. But I want to dig into the why. What is the root cause? Why does a single cell become the short stave in the barrel in the first place?
The expert analysis in the document points back to something we discussed earlier, the formation of dendrites, but it adds a very specific and highly controversial context here.
Yes, the document details how specific charging habits can create a weak cell. It explicitly states that repeated, shallow charging cycles can trigger the growth of metal dendrites, which eventually pierce the separator and create a high-impedance micro-short circuit inside the cell.
And this micro-short leads to what engineers call massive high self-discharge.
Additionally, if this single cell is located in an area of the pack with poor local heat dissipation, its SEI layer will grow excessively thick, severely shrinking its true capacity.
Okay, wait. I need to aggressively push back on this point right here.
Go for it.
Because if you read any consumer tech blog, if you listen to phone manufacturers, or even read the manuals of some EV companies, the golden rule of lithium-ion batteries is always shallow charging is better.
Everyone says follow the 20 to 80% rule.
Right. Don't charge all the way to 100%. Don't drain it down to zero. Keep the charge cycles shallow in the middle of the pack to prolong the battery's life.
That's the conventional wisdom.
But this hardcore engineering document is specifically citing shallow charge cycles as a root cause for growing dendrites and causing catastrophic microshorts. How do we reconcile this? Is the 20 to 80 rule just a massive consumer lie?
That is a brilliant observation, and it highlights exactly why reading a high-level engineering document requires critical nuance. The short answer is no, it's not a lie, but it is a massive, oversimplified generalization.
Okay, unpack that.
When consumer blogs say shallow charging is good, they're referring to the fact that keeping a battery in the middle of its state of charge, say, hovering between 40% and 60%, exerts less baseline chemical stress on the cell than forcing it to hold a full 100% charge or draining it to absolute zero.
Okay, so that general principle is true.
It is. However, what this engineering document is analyzing is the mechanical and chemical reality of repeated, highly localized stress under very specific, abusive conditions.
Walk me through that. What specific conditions make shallow charging dangerous?
Imagine a driver who is constantly shallow charging in a very specific high-stress window. For example, imagine an Uber driver who repeatedly pulls into a high-speed DC fast charging station in freezing winter weather, plugs in, and charges the car just to go from 70% to 80%, unplugs, does a ride, and comes right back to do it again.
Oh, wow. They're just sipping fast power over and over at the top end of the battery.
Exactly. When you do that repeatedly, especially with fast charging, the battery doesn't have time to properly distribute the immense heat being generated, nor does it have time to evenly distribute the lithium ions across the graphite anode.
They get bottlenecked.
The ions begin to bottleneck at the surface of the anode, which triggers that localized lithium plating we talked about, leading to dendrite growth.
But there is another problem with only ever shallow charging, isn't there? It messes with the car's brain.
That is the second, perhaps more insidious problem. It involves how the battery management system calibration works. The BMS software relies on occasional deep charges and deep discharges to recalibrate its mathematical models.
It needs to find its baseline.
Right. It needs to periodically see what true 100% looks like and what true 10% looks like to understand the boundaries of the battery. This process is heavily tied to something called top balancing.
What is top balancing?
Because of tiny manufacturing variances, no two battery cells are exactly identical. Some charge slightly faster than others.
Sure, that makes sense.
When you charge a car all the way to 100%, the BMS engages in top balancing. It gently bleeds off a little bit of energy from the cells that hit 100% first, allowing the slower, lagging cells to catch up until every single cell in the pack is perfectly equalized at the exact same voltage.
It ensures all the staves in the wooden barrel are exactly the same height.
Precisely. But if a driver only ever shallow charges, if they rigorously keep the car between 30% and 60% and never plug it in overnight to hit 100%, the BMS never gets the opportunity to perform that top balancing routine.
Oh, I see.
Over months and years of driving, the software's estimation of the individual cells begins to mathematically drift.
The map stops matching the territory again.
Yes, the BMS might mathematically calculate that cell number 45 is at 60% capacity, when in physical reality, it's only at 40%. Because the cells become unbalanced, that single physically weaker cell ends up getting overworked every time you accelerate while the healthier cells coast.
Because it's overworked, it gets hotter.
And because it gets hotter, its SCI layer thickens even faster due to poor heat dissipation. And eventually, the stress causes microshorts, leading to high self-discharge. It essentially tortures itself into becoming the shortest stave in the barrel.
So the nuance here is critical. Shallow charging slowly on a home charger in the middle of the battery's capacity is fine for general health. But aggressive, repetitive, shallow fast charging, especially in extreme temperatures, while simultaneously never letting the car hit 100% to balance the pack, is exactly how you create a weak cell and trigger the wooden barrel effect.
That makes so much sense when you lay it out like that.
It is entirely about localized thermal and electrical stress. And the tragedy of the weak cell is that once that microshort circuit forms and the high self-discharge begins, the damage is permanent.
You can't undo it.
Even when the car is parked in your driveway and turned completely off, that weak cell is slowly, continuously bleeding energy internally. converting its stored power into parasitic heat. It's an internal hemorrhage that will eventually ruin the entire pack.
Which transitions us from a localized injury to a systemic terminal illness. We are moving from the failure of a single bad cell to the inevitable, unavoidable death of the entire battery pack over time.
The macro age.
Right. The document highlights two very specific fault codes regarding this macro aging, P0A7F and BMS067. Let's look at P0A7F first.
P0A7F is the code for capacity attenuation. This represents the macro aging of the entire high-voltage system. This is what happens even if you are the perfect driver, even if you balance your cells perfectly and never fast charge in the cold.
Wait, really? How does the car actually know it's getting old? Does it have, like, an odometer just for the battery?
In a way, yes. The BMS software tracks the total energy throughput over the entire life of the vehicle. It uses two primary methods, amp-hour integration and dynamic OCV, or open circuit voltage, calibration.
Okay, let's break those down. Amp-hour integration sounds like it's just counting the electricity.
It acts exactly like a meticulous accountant. Every single time you step on the gas, it counts the electrons flowing out of the battery. Every time you hit the brakes and regenerate power or plug into a wall, it counts the electrons flowing back in.
Wow, it tracks everything.
Over years and tens of thousands of miles, it maintains a running tally of exactly how much energy the pack can physically hold.
And what is dynamic OCV calibration? How does open circuit voltage act as an accountant?
Open circuit voltage is the resting voltage of the battery when it is doing absolutely nothing when the car has been parked and asleep for several hours, and the internal chemistry is completely settled.
Just totally at rest.
The resting voltage is directly correlated to the true chemical capacity of the battery. So the car's computer wakes up occasionally in the middle of the night, measures the deeply settled resting voltage, compares it to its amp-hour electron count, and adjusts its calculation of the battery's true maximum capacity.
And eventually that capacity shrinks.
Yes. When the system calculates that the pack can now only hold between 60% and 80% of its initial rated capacity from the factory, it crosses a threshold and triggers code P0A7F. It hits what the industry calls EOL, or end of life.
And we should clarify for you listening, end of life does not mean the car suddenly bricks itself and refuses to move, right?
Correct. It simply means the battery has degraded past the threshold for safe, reliable, high-performance automotive use. The range will be severely diminished, and it can't deliver the torque it used to.
At this point, the pack must be replaced in the car.
Though it can often be repurposed for secondary ladder use, like acting as a stationary solar power storage bank for a house where the demands for sudden power are much lower.
But the document dives deep into the why behind this inevitable death. Why does the capacity always shrink? It points back to two usual suspects. The first is that SEI layer we discussed.
Yes. Over thousands of miles and thousands of charge cycles, that protective guitar callus just keeps getting thicker and thicker.
And remember, every time it thickens, it permanently traps more active lithium ions inside its structure. Engineers call this phenomenon LLI, loss of lithium inventory.
Loss of lithium inventory. I picture it like a bucket of water with a sponge sitting in the bottom. The bucket represents the battery, the water is the energy, and the sponge is the SEI layer.
Oh, I like that visual.
Over time, that sponge just keeps absorbing water and getting bigger and bigger. Eventually, the sponge is taking up half the bucket, and you can't wring the water out. The physical space to hold usable liquid has disappeared.
That is an excellent visualization. The literal physical amount of freely moving, usable lithium inside your battery decreases over time.
But there is a second, much more violent reason for capacity attenuation. Extreme thermal cycle fatigue.
Expanding and contracting.
Yes. Heating up to high temperatures while driving on the highway and cooling down to freezing overnight. Doing that thousands of times over years causes microscopic physical stress fractures in the cathode and anode materials.
That sounds bad.
The engineering document actually uses a very specific stark phrase to describe this. Actual lattice collapse.
Actual lattice collapse. It sounds like a bridge falling down.
At an atomic level, that is exactly what is happening. The complex crystalline structure of the metal inside the battery, the scaffold that holds the lithium ions, physically crumbles and collapses in on itself due to the constant thermal expansion and contraction.
Once the lattice collapses, that section of the battery is permanently dead.
Right. It's just gone.
It's happening so slowly, completely silently, underneath the floor of the car over years. But the document details what happens when this degradation goes too far. When the capacity drops even further, past the 80% mark, the car reacts dramatically.
This brings us to the code BMSA 067, Extreme Attenuation Limit.
This is where we see one of the most fascinating and aggressive system defense mechanisms in modern automotive engineering. We talked about how the extended Kalman filter and algorithms like incremental capacity analysis are constantly tracking the slow molecular decay.
Right, the Apollo math tracking the crumbling lattice.
Yes. When these algorithms calculate that the pack's overall capacity has plummeted below 70 to 75%, a critical safety threshold is crossed. The engineers know that at this extreme level of degradation, the internal resistance of the cells is incredibly high, and the structural integrity of the anode and cathode is severely compromised.
Because of this, the thermal stability of the battery becomes highly unpredictable and extremely dangerous.
Meaning, if you push the battery hard in this state, it is a massive fire risk.
The probability of a catastrophic thermal runaway event skyrockets. So how does the vehicle's brain react to this information? It doesn't just flash a polite warning light on the dash and hope you drive gently.
No, the software takes absolute control and forcibly castrates the physical capabilities of the car.
That is the exact word I wrote in my notes when I read this.
Yeah.
It neuters the vehicle. Walk us through exactly what the software does to the physical driving experience when it detects this extreme attenuation limit.
It executes a multi-tiered, non-negotiable defense protocol. First, it permanently limits the vehicle's top speed.
Okay.
Second, it initiates severe power degrading. This means it aggressively slashes the amount of torque the electric motors are allowed to request from the battery. You could floor the accelerator pedal to the floorboards, and the car will accelerate with the lethargy of a golf cart.
It flat out refuses to pull large amounts of current.
Because pulling high current through highly resistive, structurally degraded cells generates massive, uncontrollable heat.
It's restricting the flow of energy to keep the battery from boiling itself alive.
Exactly. But the most extreme measure it takes is restricting the charge limit. The software will hard lock the maximum state of charge to just 50%.
50%, that's it.
You can plug the car into a high-speed supercharger, leave it there all weekend, and the computer will physically command the contactors to open and refuse to accept any energy once the battery hits half capacity.
Because charging that upper 50%, pushing those final lithium ions into a crowded, degraded anode is where the absolute most internal pressure and heat are generated inside the cell.
It refuses to let the battery enter the danger zone.
I have to say, looking at this from a consumer perspective, there is something incredibly eerie about this mechanism.
Eerie how?
Think about it. Your car, this machine sitting quietly in your driveway, is constantly performing complex math to analyze its own internal chemistry. It calculates that its own atomic structure is collapsing and becoming thermally unstable.
It's aware of it.
It senses its own mortality and the very real fire risk it poses to the humans inside it. So, without asking for your permission, it quietly neuters its own performance. It slashes its own range in half. It takes away its own speed and torque, all to keep you safe from the dying chemical reaction underneath you.
It feels almost biological. It's like a human body sensing a massive systemic infection and shutting down non-essential organs just to survive the night.
That is a profoundly accurate way to look at it. The software is acting as a relentless immune system, protecting the physical world from the limits of chemistry.
But sometimes the physical failure happens too fast for the slow macro-aging algorithms to catch it in time. And that brings us to the final and perhaps most dramatic physical manifestation of these chemical limits.
The document calls it the voltage cliff.
The voltage cliff. This involves fault codes P0B24 and P0AC4. This is what happens when the physical internal resistance of the battery suddenly and violently breaks the mathematical laws of the car's software. Let's look at the first code, P0B214, dynamic internal resistance distortion. Paint the picture for us. What is the actual phenomenon a driver experiences here?
Imagine you are driving on a two-lane country highway. You get stuck behind a slow-moving semi-truck. You see a clear passing lane ahead. You pull out, and you violently slam your foot down on the accelerator pedal to pass the truck quickly.
In a powerful EV, that action demands a massive, instantaneous surge of energy.
In engineering terms, you are demanding a massive dynamic transient load. The electric motors are suddenly asking the battery to deliver huge power, pulling perhaps 600 amps of current instantly.
600 amps is a staggering amount of electrical force to move in a fraction of a second.
It is immense. Now, in a perfectly healthy battery pack, when you demand 600 amps, the overall voltage of the pack will droop or drop slightly under that heavy load that is normal, expected physics, but it will successfully deliver the power and you shoot past the truck.
But in a battery suffering from dynamic internal resistance distortion, something terrifying happens.
The cell voltage begins to oscillate wildly,
Yeah.
behaving completely outside the parameters of the mathematical ECM prediction. And then the voltage instantly crashes down past the safety limit, plummeting to what engineers call the UVP, the undervoltage protection threshold.
This is the voltage cliff.
Yes, you step heavy on the pedal to pass the semi-truck, demanding maximum power. But instead of surging forward, the voltage drops off a cliff. The battery management system sees the voltage crash, panics to protect the system from a catastrophic failure, and instantly cuts all power to the motors.
You lose all propulsion in the middle of passing a truck.
That is a nightmare scenario. But why does it happen? What is the actual physical root cause inside the battery that makes the voltage crash so violently under load?
It comes down to severe internal polarization, which in this context is almost always caused by... Yes, it's exactly like trying to force the water volume of a massive fire hose through a tiny, cracked drinking straw. To understand why the voltage crashes, you just have to look at Ohm's law, which states that voltage drop equals current multiplied by resistance, or V equals I times R.
Okay, let's apply the math to the cracked weld.
If you have a microcrack in a laser weld, the electrical resistance R at that specific microscopic point spikes dramatically. When you are just cruising at 30 miles an hour, the current I is low, so the voltage drop is small and the car drives normally.
But when you slam on the accelerator to pass that truck, you suddenly demand 600 amps of current to flow across that cracked weld.
A massive current multiplied by a massive resistance
Equals a massive instantaneous voltage drop. The voltage crashes instantly, not because the chemical battery is empty, but because the physical copper highway delivering the electricity has a microscopic fracture in it.
The software sees the voltage plummet to dangerous levels. It also knows that forcing 600 amps through a high-resistance crack will generate so much localized heat that the weld will instantly glow white-hot, melt, and ignite the surrounding plastics.
So the software violently cuts the power to save the car from catching fire.
The voltage cliff, a microscopic, invisible crack in a laser weld, takes down a 2-ton high-performance vehicle in a split second on the highway. That is incredible.
It really is. Let's look at the final code in our journey today, which is closely related to resistance. P0AC4. DCIR too high. Direct current internal resistance too high.
This is a comprehensive, overarching mother code in EV diagnostics. The BMS doesn't just wait for you to floor the accelerator to test the resistance. It is constantly actively testing it.
It uses a very specific mathematical test, calculating the change in voltage over a change in current, or a pulse response to continuously monitor the battery's internal resistance.
How does that pulse response actually work in plain English? What is the car doing?
Imagine you are walking a large dog on a leash, and you want to know how much resistance the dog is going to give you without actually trying to drag it down the street.
Okay.
You might give the leash a tiny, quick, sharp tug, a stutter step, and gauge exactly how hard and how fast the dog pulls back. The car does the exact same thing with electricity.
It gives it a little tug.
It sends a tiny, microsecond stutter step of electrical current, a pulse into the battery, and precision sensors time exactly how long it takes the battery's voltage to react and push back. By measuring the delay and the voltage change, the software can calculate the exact internal resistance of the chemistry.
That is brilliant. It's constantly testing the tension on the leash. And if it calculates that the internal resistance has jumped, say, 50% above the factory specifications, it triggers the P0AC4 code. And what does the car do?
It acts just like it does for extreme aging. It forces a massive instantaneous redraw of the stated power map. It immediately triggers power derating. The car slows down, the torque is drastically restricted, and you are forced to limp home.
But the physical root cause for this specific code is fascinating, because it's not just about old age or cracked laser welds or abusing the car. The document highlights a massive external environmental factor that triggers this code.
Extreme cold weather.
Yes. We have to remember that temperature is the master switch of electrochemistry. Inside a lithium-ion battery, the lithium ions physically swim back and forth between the anode and the cathode through the liquid electrolyte solvent.
But when the ambient temperature drops well below freezing, the physical properties of that liquid solvent change drastically. The viscosity of the liquid spikes exponentially.
Viscosity, meaning the thickness of the fluid?
Much thicker. The engineering text literally describes the electrolyte in extreme cold as acting like frozen syrup. The liquid becomes so incredibly thick and viscous that it physically blocks the diffusion pathway of the lithium ions. They try to swim, but they are stuck in the syrup.
Because the ions physically cannot move through the frozen liquid, the resistance to the electrical flow skyrockets.
Exactly. So it's a harsh winter morning. It's 10 degrees below zero. The car's been parked outside all night. You get in your EV, you hit the accelerator to pull out onto a fast-moving road, and the car's pulse response instantly calculates, nope, the internal resistance is up 50% due to the cold.
It immediately derates your power to protect the cells from damage.
But in this case, the battery isn't permanently broken, and it hasn't chemically aged. It's just frozen. Once it warms up, the syrup thins out, the resistance drops, and the power comes back.
Precisely. The system is protecting the battery from your demands while it's in a vulnerable physical state.
Though the document does meticulously note that code P0AC4 can also be triggered by permanent physical degradation, things like severely aging electrodes, or something as simple as insufficient torque on the mechanical screws holding the heavy copper bus bars together.
Or severe oxidation, essentially rust forming on the contact surfaces between modules. Any of these physical flaws increase electrical resistance, and the BMS will respond the exact same way by restricting power to protect the system from heat.
Which brings us to the end of our incredibly deep dives today.
It does. Let's take a moment to summarize the astonishing journey we have just taken. We started with a concept that every driver is familiar with: a simple, annoying warning light on a dashboard. But we've traveled all the way down to the molecular level of an electric vehicle.
We've seen exactly why the legacy check engine mentality and legacy OBD scanners are completely blind to the realities of a living, breathing, decaying chemical system.
We walked step by step through the elite four-piece closed-loop analysis, moving from macro-level sandblasted explosion valves down to corrosive liquid electrolyte creeping up wire harnesses, fighting gravity like a capillary siphon.
Down to scanning electron microscopes, hunting for razor-sharp lithium dendrite spikes, and finally up into the cloud data where Apollo-era Kalman filter algorithms calculate mathematical residuals to predict invisible decay.
We explored how engineers map this chaos using the rigid five-dimension MECE architecture. We looked at how a single weak cell, caused by localized thermal stress, can trigger the wooden barrel effect and drag an entire vehicle into limp mode.
We saw how years of thermal fatigue cause actual atomic lattice collapse, leading the car's artificial intelligence to essentially castrate its own power and charge limits to prevent a catastrophic fire.
And finally, we looked over the edge of the voltage cliff, where microscopic cracks in laser welds and frozen, syrupy electrolyte can cause a massive voltage drop, violently stripping your car of power in a split second on the highway.
For you, the listener, the ultimate takeaway here is a total paradigm shift in how you view the machine in your driveway.
You now know that when a modern EV fails, or limits its power, or throws a warning code, it is rarely just a simple computer glitch that needs to be reset.
What you're actually witnessing is a high-stakes, real-time battle between highly advanced software algorithms desperately trying to contain, manage, and predict the absolute, unyielding limits of physical chemistry and structural degradation.
It is an incredibly delicate, continuous dance between code and chemistry. And this reality raises a very important question, a final provocative thought for us to ponder as we close this deep dive.
I love this question. As our battery management system software, our machine learning models, and our extended Kalman filters get smarter, faster, and exponentially more predictive,
Are they actually extending the physical, chemical life of the battery? That is the million-dollar question. Are these brilliant algorithms actually curing the disease of chemical decay, or are they merely getting exceptionally good at managing our expectations?
Are they just quietly, invisibly degrading the car's performance in the background, carefully hiding the battery's inevitable, irreversible chemical death from the driver until the very last possible second?
Are they preventing the end or just managing the hospice care flawlessly? It brings us right back to where we started. When you look at an EV dashboard, you aren't looking at a clean binary X-ray of a broken steel bone.
You are staring into the murky, incredibly complex waters of a degrading chemical organism.
And as we've seen today, the deeper you look into those waters, the more fascinating it gets. Thanks for joining us on this deep dive.